Good afternoon, everyone. I am here for the first live session for this ongoing MOOCs course, Fundamentals of Nuclear Power Generation. I guess you already have completed quite a few weeks in this particular course. Like, if I understand here properly, then we have already completed 4 weeks and into the fifth week of this particular course. And you guys probably have already got hold of whatever is going on, whatever is being taught as a part of this course over all these weeks. Just hold on, please. Okay. Uh, so so far we have completed a few modules of this particular course, and I think it's going on quite well because we have not received too many queries in the course portal till date. Whatever queries we have received, we have tried to respond to that, but the number of queries that we have received are very less till date, and that's why I can only assume that you don't have too many queries that you may be required to ask, or you may be interested in asking to me. Even in the Excel sheet that was shared as a part of the preparation for this live session, there also I have got only very few queries, only a couple of them, which I shall definitely be responding. In addition to that, if any of you are having any query related to this particular course, the content that we have already covered, if any query you have, please ask in the live portal, and I shall be available here to respond to those queries immediately. Yes. Now, as I wait for your questions from your side, probably I can have a quick review of whatever we have done in this course till date. Like this course, as the name suggests, is a primary course or an initial level course on the topic of nuclear power generation. So we started talking about the fundamentals, the overall scenario, the national and international scenario of nuclear power generation, the present power requirement as well as the power resources available with us. In the first week, therefore, we had at least quite general kind of discussion, gradually went into slightly more involved discussion about the atomic structure, the concept of the nucleus of an atom, the Bohr-Rutherford model, which specifies primarily two parameters to characterize the nucleus of any particular isotope, that is the mass number and the atomic number, which basically are mass number, or rather atomic number, is the number of protons present in the nucleus, and mass number is the total number of nucleons, that is the total number of protons plus neutrons present in the nucleus. And using these two numbers, we can characterize any particular isotope. Then you got the concept of mass defect, that is, once we combine the mass of the protons and neutrons present in the nucleus, then it has always been found that the combined mass, or this theoretical mass, is always higher than the actual mass of the isotope itself. And the difference between these two quantities is called the mass defect. And once we estimate the energy corresponding to this lost mass or mass defect, that energy is referred as the binding energy, which can loosely be viewed as the amount of energy required to keep the nucleus together within a very, very small space. All the protons being positively charged, if we are talking about a nucleus having multiple number of protons, these protons will always experience a strong repulsive force because of the identical nature of their charge, and so we must need some strong force to bind these nucleons together, and binding energy provides us an estimate about the amount of force that is required to bind those nucleons together. Of course, we have not talked about the nature of this force, or the so-called the strong nuclear force or strong interaction, which requires some understanding of quantum physics that we have not talked, because the focus of this course is more on power generation, and so I have not gone into that much detail about the structure of nucleus or quantum physics point of view. In the second module, in the second week of this course, you got the concept of radioactivity. Radioactivity, as has already been defined, is a characteristic, a very interesting characteristic displayed by only certain nucleus or certain isotopes, where the nucleus itself is inherently unstable, and they can decay spontaneously, resulting in the formation of some new nucleus. Now, the new nucleus can just be an isotope of the original nucleus itself, or it can be an isotope of a completely different element. And whenever there is such a disintegration or decay is taking place, that always is accompanied by emission of certain particles, maybe an electron or positron, and maybe some other kind of particle like alpha particle, or it can also be accompanied by emission of gamma rays. And in most of this decay are associated with some loss of mass. That is, the combined mass of the product side is less than the mass on the reactant side, and that lost amount of mass gets converted to energy. However, we may be having some radioactive reactions where the combined mass of the product is higher than the mass of the reactants. In that case, energy gets converted to mass. However, the number of such reactions or such examples are less. Such endothermic radioactive reactions are less in number. Most of those are exothermic in nature. That is where the mass gets converted to energy. Now, radioactivity is purely a natural phenomenon, and it's a characteristic of that particular isotope. Even the radioactive characteristics of two different isotopes of the same element can vary substantially. Like you know by now that the radioactivity is measured by half-life or the decay constant. You can use any one of them because they are a very straightforward relationship between them. Half-life is the one that is commonly used. Higher the half-life, lower is the rate of decay because the decay constant is inversely proportional to the half-life. Now, if we talk about two different isotopes of the same element, like if we pick up uranium 235 and 236, their half-lives are substantially different. Uranium 235 is something that is naturally available in the natural uranium ore, and it has an extremely long half-life, whereas uranium 236 gets produced only during certain radioactive reactions, particularly when a uranium 235 absorbs a neutron. Similarly, when an uranium 238 absorbs a neutron, it produces uranium 239. Uranium 238, I can't remember exactly, but has a half-life, I think, of the order of 10 to the power 10 years, whereas uranium 239 has a half-life of a few minutes only, and therefore it almost immediately disintegrates to produce something else. Accordingly, different radioactive isotopes displays different decay characteristic, different radioactive characteristics, and also the nature of their decay are completely different. You have got some idea about what can be the probable type of radioactive decay for an isotope using that N by P ratio. Like we know that as the number of proton keeps on increasing in a nucleus, we generally need more neutrons to cover up, and that N by P ratio keeps on increasing as we go to higher atomic number. However, if the number of neutrons are too high or too low, then we may have different kind of radioactive decay. In some case, we may be having the beta minus, so-called electron decay. In the other case, we shall be having the beta plus or positron decay. Whereas if the atomic number is very high, that is the number of nucleons are very high, particularly when the atomic number goes beyond 80, we generally have the alpha decay, where the nucleus ejects an alpha particle, which is nothing but a helium nucleus, two neutrons and two protons, and accordingly gets converted to something a bit lighter. But this is natural radioactivity which happens without control of any external factors. We can't control the rate of radioactive decay of a natural radioactive isotope by changing any of the controllable parameters like pressure, temperature, etc. have no influence on the half-life of an isotope. And there the concept of artificial or induced radioactivity comes into picture, where an isotope which may originally be radioactive in nature, which may not originally be radioactive in nature, we force it to interact with some particle, and accordingly we have some kind of interaction, and after that particle nucleus interaction we have some product which is naturally radioactive. That's what we refer as the induced or artificial radioactivity. Now to induce such kind of behavior, we can use neutron, we can use protons, etc., or alpha particles, but neutron is the most common choice. The reason for that we have already explained as a part of these lectures. Now, artificial or induced radioactivity again can have multiple types. Particularly, the neutron nucleus interaction can lead to multiple kind of interactions. We generally have three broad groups of interaction. One group of interaction is the collision or scattering interaction, which can again be subdivided into elastic collision or elastic scattering and inelastic scattering. Then we can have the absorption kind of interaction. Absorption can be categorized into the capture or non-fission capture and fission. During non-fission capture, the nucleus just absorbs the neutron and produces an isotope of itself, whereas during a fission reaction, the neutron nucleus combination produces a temporary nucleus for an extremely short period, can be something of the order of 10 to the minus 15 second, and then that breaks to produce two fission fragments. Commonly, we shall be having two fission fragments, that is, two isotopes having substantially different mass number. In some rare cases, we may have a third one. Plus, these fission fragments will also be accommodated, or I should say, accompanied by emission of certain neutrons, gamma rays, and sometimes in certain other particles as well. During fission reaction, a substantial amount of mass that gets lost, and accordingly, every fission will produce significant amount of energy. Like a single fission of an uranium 235 isotope can produce around 170 180 MeV of energy, plus the fission fragments that are produced, they are naturally radioactive, and their radioactive decay will contribute some further amount of energy over a longer period of time. And combining all those, a single uranium 235 isotope can produce about 200 MeV of energy after fission. There is a third kind of neutron nucleus interaction also, the charged particle interaction, which we have covered, where which generally is not associated with nuclear reactors but happens primarily with lighter isotopes, where after the interaction we may have emission of 2 or 3 neutrons or sometimes alpha particle or protons, etc. But again, those are generally not something that we observe in a nuclear reactor. In a typical nuclear reactor, there are three kinds of interactions that are important. The elastic scattering, which leads to or which is used in the moderation process. You have already gone through a detailed theory of moderation, the theory of elastic scattering, where we have got mathematical relationship to estimate the amount of energy lost by neutron in a single collision, and then the idea of logarithmic energy decrement, which provides a way of to estimate the average reduction or average decrease in the energy of a neutron, considering all possible direction of deflection. Then the second important interaction is the capture. All isotopes, most of the isotopes present in the world will capture neutron during an interaction. Now, capture generally is an unwanted one. However, certain capture reactions lead to the breeding. That is, a fertile isotope can absorb a neutron and produce a fissile one. Uranium 238 absorbs a neutron and after two stages of beta decay produces plutonium 239. So this breeding reaction is a very important and useful one. And the second use of the non-fission capture is in controlling the rate of reaction, where we use materials something like boron, cadmium, gadolinium, etc., which has generally high capture cross section, and by suitable use of some structures like rods or plates made of these materials, we can control the rate of nuclear reactions. And the third use is, of course, fission. We have also gone through detailed understanding of the neutron life cycle in the fourth module, where you have seen different phenomena that a neutron may undergo inside a nuclear reactor. It starts as a fast neutron. We may have some fast neutron fission, then it goes to the moderation process, during which some neutron gets captured. Particularly the resonance absorption is a very important phenomena. Even after becoming thermalized, some neutron may get captured by other material, the structural material, the moderator itself, the coolant, control elements, etc. And finally, we shall be having the thermal fission. During every thermal fission, we have production of some more neutrons, and combining all these factors, we can define the effective multiplication factor and the the reactivity of a nuclear reactor. Now, for smooth, stable power production, we want the multiplication factor to be 1 or reactivity to be equal to 0. However, during the initial part of a nuclear reactor operation, means when the reactor is starting from cold condition, we want reactivity to be positive so that the rate of reaction keeps on increasing till we reach the desired level. Whereas when you want to shut down a running reactor, we want the rate of reaction to keep on reducing, that is, we want to maintain a negative reactivity value or multiplication factor less than 1. So in the fifth week, we have started talking about the thermal hydraulics, that is how the coolant captures or absorbs the energy produced by fission. And we are talking about two different examples. the plate type reactors and the cylindrical reactors, and some mathematical analysis has already been done as a part of this. Now, going to the questions that we have faced, one question was about the book which we should refer for this course. Now, I think along with the syllabus, some of the suggested books have already been mentioned in the course portal. So please check from there. You may not be able to purchase any of these books, but I guess you'll be able to manage these books from online sources. You can download the soft version of these books from certain websites. So please check that out. Another question that is more technical is someone is asking, Avinash Mishra has asked that the mass of electron, which is in the range of 10 to the power minus 31 kg, in the lecture during beta decay, we take mass of electron as 0. This is not truly correct because we have not taken the mass of electron to be 0. Think about what happens during a beta decay. During a beta decay, one isotope emits one electron, but that electron is not coming from the orbits, rather this electron is coming from the nucleus. Inherently inside the nucleus, one neutron gets converted to a proton and an electron, and also there will be emission of antineutrinos. Now, the mass of neutron is higher than the mass of proton. In fact, the mass of neutron is higher than the combined mass of proton, electron, and the antineutrino. So there will be some amount of mass loss. However, while calculating that amount of mass lost, we have not at all rejected the mass of or ignored the mass of the electron. You can definitely, or I think you should consider the mass of electron during that calculations also. So in order to estimate how much energy gets produced during a typical beta minus decay, you should subtract the mass of proton and electron from the mass of the neutron. Mass of the antineutrino is too negligible, and we should ignore that. Now, if we think from practical point of view, typically the mass of one one neutron and one proton both are of the order of 1 mu, with mass of neutron being slightly higher, of the order of 10 to the minus 27 kg, whereas the mass of an electron is 4 order lower than that. So while I agree that we must consider the mass of electron, but in case we are ignoring the mass of electron also, the final mass defect value that we will be getting, that will not change that much. Just like that, using the equivalence of mass and energy, we know that 1 MeV of mass is equivalent to 931 MeV. So accordingly, the mass of one proton and one neutron is around 940, 950 MeV. The exact value you can calculate. Whereas the amount of energy associated with an electron is less than 1 MeV, actually 0.5 MeV, around that. And therefore, even if we are ignoring the mass of the electron, then estimation of the total energy lost will, or estimation of total mass lost or energy produced will not differ that much. I have also received one query which came to me via mail and not using our portal. There, someone has asked that the notes which are available in the course portal, I am not sure from where he or she has accessed those, but mentioned that those are only transcripts of the lectures and asked about lecture slides, etc. thing. I'll try to share that. I have to check the procedure. I have to check at in what mode I can share those, but if allowed, I shall be able to share those with you. Now, so far in the live portal, I have not received any query. I'll wait for a couple of more minutes to see if anyone is asking any question. If you are having any query, please write it here, because it's always great to have a direct interaction with you. However, if questions are not coming, then I have to stop this live session. Moving forward, in the coming weeks, you will be introduced to some more concepts. Like we have a very interesting concept of control of the nuclear reactions, where we shall be talking about the role of the prompt and delayed neutrons. Now, the neutrons which are involved in the operation of a nuclear reactor, they can broadly be classified into two categories: prompt and delayed neutrons. Prompt neutrons are those which are produced during the fission itself. You know that during every fission, some neutrons are produced, typically 1 to 5. In some cases, it can be 1, some cases 2, very difficult to predict. It can be as high as 5 also. Like for uranium-235, considering a very wide database, it has been estimated that every fission of uranium-235 on an average produces 2.42 number of neutrons. Those neutrons are referred as the prompt neutrons. However, the fission fragments which are produced, like after the isotope gets broken during fission, we have two different isotopes produced. Like for uranium-235, we know we shall be having one isotope having mass number around 135, other having mass number in the range of 96 or 97. Uh, but the neutrons which are getting produced from that, those are prompt neutrons, as I just mentioned. Now those two fission fragments, both of those are naturally radioactive, and they will go through their own steps of radioactive decay. Each of them can have quite a long chain, means it's just not just 1 or 2 steps that they will achieve a stable condition. They may go to 6, 7, 8, 10 steps to finally reach some kind of stable isotope, and during some of those steps we may have emission of some more neutrons. So those neutrons are emitted much later on, because when those neutrons will be emitted, that will depend upon the decay rate of those fission fragments, and these neutrons are called delayed neutrons. While they are appearing much later on, and therefore they don't have much role in sustaining the chain reaction, they have a very important role to play in controlling the rate of reactions, as we shall be discussing in the subsequent module. Then we have modules on the design of reactors, different kind of nuclear reactors, the pressurized water reactor, boiling water reactor, PHW or can-do reactors, the fast breeder reactors. We have a module on the process of breeding or fast breeder reactors. We have a module on fusion process also. So all these will be coming in the future weeks. Now I've just got a question coming in the portal, which is where question is about the course exam. Will the exam be similar to the assignments, or can we expect long answers or the history and context you discussed during the lecture? No, it will be somewhat similar to the assignments, but of course, it is not that the assignment questions will directly be repeated. Yes, it will not be long answer because your final exam will be computer based, where you have to either means some of the questions will be of MCQ type, whereas some of the other questions will be problem based, where you have to write the answer to the problem on a provided box, just like you are doing in the assignments. So in that way, these are similar to the assignments, but just not repetition of the assignment questions directly. Rather, different type of questions will be there. So you probably have noted that in each of the module towards the end, I have tried to discuss some mathematical problems, some numerical problems. So you try to cover those to get an idea about what are the types of problems that can be solved from those topics, and accordingly from those topics, and accordingly you can think of some more problems and be prepared for this. Those kind of questions will be there in the exam. But I shall definitely not be asking you something about the history of nuclear reactions, etc. This. So any other query? If I'm not having any query, then probably I'll close down this session. But even if you are not having any live session, you can still reach out to me through the course portal, and also you can send mails to me, and I shall be happy to respond to those. So yeah. So fine. Yeah, I have already answered to the question that came on the YouTube portal for this. So in that case, I'll close down this session. Whoever has participated, thanks to all of you. We shall be meeting again in the next live session. And as I have just mentioned, you can always reach me through mail and also through the course portal. Thank you very much. Have a good day.